Alright, we're just going to take a quick delving into a bit of an IB topic, so it's not really a complicated one. So in this equation, this v equals 2 pi r over t, which we derive from uniform motion, and again, using circumference and period, sometimes you're going to see it written a little bit like this. You're going to see it as this v equals this symbol times r. So this symbol here, this is the lowercase omega. It's a Greek letter. It kind of looks like a really curvy W. But yeah, so we could say that the speed is equal to this omega times r. And then of course we're going to define this omega as 2 pi divided by t. And you know, if we wanted to use the relationship for period and frequency, so like t equals 1 over f, we could also put that in there and we get something that looks like omega equals 2 pi times f. Both the same thing. This quantity here, this is referred to as the angular velocity. For us, we can also just refer to it as angular speed since we're strictly dealing with magnitude. And as we mentioned, we're dealing with that Greek letter omega. So the units for angular velocity are this radians per second. Now, just to give you some context on radians, for us, when we measure, a circle, like if I kind of measure out a circle and I go around, we'd say that that's 360 degrees. And that's what we're very much used to. Another method of measuring angles, instead of writing 360 degrees, and this is like the more mathematical way of doing it, and you'll see this in certain math courses like Math 30. Instead of 360 degrees, they're going to call this 2 pi radians. So 360 degrees is the same thing as saying 2 pi radians. So what they're really saying by this angular velocity of radians per second, they're basically saying how much of an angle are you sweeping out every single second. Like if I had my pen and I was trying to kind of have it trace a bit of a circle here, so if I was kind of like rotating it, the angular velocity would basically measure how much is the angle changing every second, or how much of an angle is being swept out per second. So the angular velocity, the angular speed, is kind of measuring that rate of change of that angle that's being swept out every single second. That's basically all we mean by angular velocity. There's not really much we do with it in high school, but it's just to kind of bring your attention to it. So let's just do a very quick example using angular velocity. So we got planet O'Donnell, must be a nice place. It's rotating around the star of physics. So the distance between planet O'Donnell and the star of physics is 3.69 times 10 to the 12 meters. And it takes planet O'Donnell 9,000 days to orbit the star of physics. So we're going to find planet O'Donnell's angular speed, and we're also going to find its orbital speed. So angular speed deals with omega. Orbital speed is just v. So if we know omega, we can find v. So let's find omega first. So we know that omega is just going to be 2 pi divided by t. Now, we're probably going to want this time in seconds. I didn't actually mention the units, but let's put it in seconds anyways. So 9,000 days, we need to convert that. Well, we know that there are 24 hours in a single day. We know that there are 3,600 seconds in an hour. And yeah, that's pretty much all we have to do for that. So the days are going to cancel out. Hours are going to cancel out. So we got to take our 9,000 times 26 times 3,600. And what we're going to get is that the period of this is about 7.776 times, let's see here, 1, 2, 3, times 10 to the 8 seconds. Alright, we can calculate the angular speed. So we have omega equals 2 pi over t, or we're going to do 2 pi divided by this 7.776 times 10 to the 8 seconds. So we're very careful with the calculator work. So we're going to find that it's about 8.08 times 10 to the minus 9 radians per second. So let's put this into context for a second. So just to kind of clarify on this, one single radian is about 57.3 degrees. So that's 1 radian. What this is saying is that when planet O'Donnell is orbiting the star of physics, every single second it's rotating by about 8 times 10 to the minus 9 radians. So it's sweeping a very, very, very practically insignificant angle every second. What this is telling us is that it's orbiting around the star. It's not going overly fast in that sense. But yeah, basically this is the angle it's sweeping out every single second. Now, we also know that orbital speed is just the angular speed times the radius. So we can take that angular speed, radians per second, and then we're going to multiply it by that distance of 3.69 times 10 to the 12 meters. And that is going to give us a much larger number here. So we're going to get about 2.98 times 10 to the 4 meters per second. So our angular speed is quite small because the angle being swept out is not that large, but our object's speed is still quite large. Like its linear, linear might not be the right word in this case, but like its orbital speed is still quite large. Like it's still traveling around that path at a substantial speed. Like it's traveling almost 30 kilometers per second. So that's just to show you kind of orbital speed, orbital velocity, and how we would relate that to just regular old orbital speed that we talked about.